So raise your hand if you plan to come for the picnic. Okay. All right. Okay, thank you. So then we'll continue with Balázs's last talk on graph limits.
Thank you very much. Can you hear me? Okay. So I start with two examples today. The first example is a graphon which is defined on the probability space, which is the surface of the two-dimensional or the three-dimensional ball. And the probability measure on omega is just a uniform measure on the sphere. If we consider the following graphon, Wxy is equal to 1 if and only if the scalar product of x and y is non-negative, and it is 0 otherwise. So this graphon is a very nice symmetric graphon, and there is a theorem that all standard probability spaces are equivalent, so we can represent the same graphon in a different way. So let us take a measure-preserving transformation from the unit interval to the sphere, and then I define not W but U as the graphon which is just W composed with this measure-preserving transformation. So the advantage of this new graphon is that it leaves now our familiar probability space, the unit interval, and I could even draw a picture about that. So here is the unit square on which U is defined. So U goes from here to 0 and 1. And you could actually draw a nice picture, like put a dark pixel where the value is 1 and put a white pixel where it's 0. So you would get something which looks entirely crazy here. Actually, probably it looks like a beautiful artwork or something like that. It has many small pieces, a fractal-like structure. So it's something really interesting. So if you look at, if you don't know where this graphon comes from, and you just look at it, you may think that it's something very super exciting, crazy stuff. But actually, the reality is that all the subgraph densities in U are exactly the same as in the graphon W. So the two graphons are weakly isomorphic, and the natural question arises: how can you actually figure out from this crazy thing that it's nothing but the sphere? So it's a very natural question. Also, let me mention that this graphon W is very, very symmetric. The symmetry group of the surface acts on this graphon in a natural way. It's much harder to detect these symmetries from this representation. Now, let me give you another example, which is in some sense the opposite of this. This is example 2. So this was example 1. We go back to the simplest graphon on Earth, which is just the constant graphon, which takes just the value 1/2. And also, I can look at another representation of the same graphon, then omega is just a single element probability space. And then again, uxx is equal to 1/2. This was Lotzi's diagram of this form. So now the situation is the opposite. This graphon has many symmetries, like crazy ones, like measure-preserving bisections, if you like. And this graphon has no symmetries, just the trivial one, since there is no room for symmetry. So at some point we have to make a decision if we're going to introduce symmetries for graphons. Which one do we take seriously, this example or that example? And also in the previous example, the natural question arises how to detect those hidden symmetries coming from the sphere. The third question is that if we get a graphon like that, how do we recover the most natural topological space on which the graphon is represented, if there is any? Maybe there are thousands of possibilities. And the answer to this question turns out to be really strange. The answer is that there could be that there is a nice unique topological space on which it is represented. Now it turns out that there are two natural topological spaces very closely related to each other. And I am going in that direction with my talk. But here is the meta statement. So if somebody gives you a graphon like that, or any graphon, then it turns out that there are two topological spaces associated with it, and you can always represent that graphon on those two topological spaces equivalently, but these two spaces are very, very closely related to each other. You will see. Okay, before going on, I would like to do a nice thought experiment. So we do something really applied, something which looks like a very much applied problem. And this is the following. Assume that you have a friend in another planet or other universe. And she wants to let you know how that universe looks like. So maybe the universe is 4-dimensional or 5-dimensional, but she takes many, many, many pictures and she sends you the pictures. So what you get as an information is the following. She sends a picture, so you get a sequence of not bits. In the first example, you get a sequence of intensities, like lambda 1, 1, lambda 2, 1, lambda 3, 1, and maybe lambda 10 million. And this one is here because this is the first picture that she sent. And I tell you, so these are black and white pictures, and these are the intensities of the picture of the pixels. Okay. So basically what she does is that she makes a photograph in that universe and she orders the pixels in some way, maybe in a random way, okay? And then she sends the picture in this format. I mean, most of the time this doesn't make sense because maybe the picture is 5-dimensional. So you don't know how the pixels are ordered. But assume that you don't just get one picture like that, but you get many, many pictures like that. Lambda 1, 2, lambda 2, 2, and so on. So So you get maybe thousands of pictures from that other universe or other planet. And now you want to learn about the life there. So basically what you want to do is to recover the topology of that universe from this information. So what do you do? Who has an idea? So what I'm saying is that the encoding is always the same. If she decides to send the messages in a certain format, then she repeats that. These are always the pixels ordered in some way. And you want to actually recover the nice pictures. Maybe the person lives on a Riemann surface or something like that. And the pictures looks like nice pictures on a Riemann surface. Yes? Yeah, so not necessarily randomly, but it's really like an encoding. So the person takes a picture, maybe it's a two-dimensional picture, and each pixel has some intensity. And then you fix an encoding of this picture, that this is the first pixel, this is the second pixel that you send, this is the third pixel, any. It could be like this type of encoding. Does not matter, but the encoding is fixed. Yes? Yes. So basically what you do is, you look at the columns here as random variables. So this is random variable x1, this is random variable x2, and so on. This is x10 to the 7. And if the universe is, the pictures are nice and not necessarily continuous but reasonable, then what happens is that if two pixels are closer to each other on this surface or whatever, then the corresponding pixels have a higher correlation. Okay? That's very reasonable. If you look at zillions of photographs, then if you look at two pictures that are close enough, then they correlate more than pictures that are far enough. So basically, you can recover a metric. Let me call this set V, the set of columns. And you can recover a metric space structure on this set V. So the distance of I and j is just the expectation of xi minus xj squared, say square root of that. Okay? It's basically the correlation in some sense, but not exactly. That's a metric space. Good. So we solved the first problem. We can learn about the life of this other person in the other universe, and then see nice pictures. But now here comes the second example. Now the pixels are taken with a more primitive camera, and the photographs are taken with this more primitive camera, and every pixel is either 1 or 0. But if there is some gray area in the picture, say again my example from last time. Here is the picture. You have a gray area, then it is represented by some random pattern. Okay? To make it look gray from a distance. Now, what we do is, we get messages like that. And we want to again recover the topological structure. The problem is that this type of correlation thing is not really true anymore in this model. So we want to do something which is more robust with respect to randomness. So what can we do? Any ideas? Correlation between that is, but the problem is that you want the small sets to be consistent with the topology, but you don't know the topology yet. This is what you want to recover. Okay, I tell you, because it's really a beautiful thing that you can do here. So you look at this as a matrix, or okay, I tell you two ways of interpreting this. So this is the matrix of the data, and then you construct this matrix M transpose times M, which is basically the covariance matrix, the correlation operator corresponding to these random variables. So basically the entries are just the Mij is just the expectation of xi times xj. So this is a semi-definite matrix. And then you do the previous method for this new matrix. So it's basically an iteration of the previous method, in which now you look at this new matrix M, and this is a V cross V matrix. The values are actually continuous now, so they can take values between 0 and 1. And then you repeat the previous procedure for this new matrix. And it turns out that it actually handles randomness in a nice way. The reason for this is that this new metric considers two rows the same, or two points not the same, but similar, if the scalar product of these two rows with any other columns, with any other column is similar. In the previous case, two columns were similar if they had a small L2 distance. In this new metric, two columns are similar if they have similar scalar product with any other column. And that takes care of this randomness. So digest this at home. I don't want to go too deeply into this example, but the thing that you should remember is that basically we apply this idea in an iterated way. First we compute this covariance matrix, and then we apply the previous idea not to this matrix, but to this new matrix. And there is one more beautiful thing, that if you compute eigenvectors of this matrix, then those eigenvectors will be basically continuous in this hidden topology. So if you look at, say, F1, F2, F3 are eigenvectors of M, then each of these eigenvectors give an embedding of the space V into the real numbers. Okay? And we think of these eigenvectors as continuous functions in the topology, especially those ones which correspond to large eigenvalues. Now, this is storytelling. You don't have to have the intuition yet why this is true. But basically, if you take the corresponding eigenvalues ordered in a decreasing way, and you take the first few such eigenvectors, then they together give an embedding of V into a bounded dimensional space. So F1, F2, and so on, Fn together give an embedding of V into a bounded dimensional space, and this embedding somehow recovers this hidden topology. And this is basically also, if you are familiar with, what is called principal component analysis. Which is believed to have a lot to do with human intelligence. When we want to pick up the main somehow features, then it seems to have something to do with principal component analysis. So there is something, I mean, many things are related here. For example, Fries and Cannon pointed out that Semiradis regularity lemma is basically principal, I mean in the weak form, not in the strong form. The weak form is basically a principal component analysis. So, I mean, what I'm saying is that all these things are related to each other in a very interesting way. Okay. Well, now I go to the more formal definition. This was really just storytelling. So I have a graphon on the probability space omega. And the idea that I get from here is that maybe I can introduce some metric space structure on omega by using this L2 distance of the rows of omega. So what is a row of omega? Is just a function. So each element x in omega is related to a one variable function, namely a random variable, which is this function. Z goes to wxz. In other words, if this is the graphon and this is the point x, I just pick this row in the graphon. And this is just a random variable. That I call x. X little x. So then, once I have these random variables, I can just say that the distance of x and y, 2 points, x and y, is the expectation of x minus x, y, squared and the square root of that. So let me write it in an integral form. So dxy is the integral of wxz minus wyz squared and the square root of this. Now there is a problem with this, if you do it this way. The problem is that this W is only defined up to a zero measure set. And I mean, there are all kinds of problems because first we don't even see that this metric space is an invariant of the graphon, and secondly, if we change the graphon on a zero measure set, then we may get new points. Like I put some row into the graphon which is absolutely unnecessary, and it adds a new point to our metric space. And if we do measurable objects, then we are very liberal about zero measure stuff. But when we do topology, we are absolutely not liberal about zero measure stuff because in the first line we want to get a topological space. And it may be infinitely many new points in the topological space. So we can't recover it really. So what we do is somehow we want to get rid of those rows which are unnecessary. But we also may add new rows which are necessary, but they are not there. And I will give you an example for this. So consider this graphon, which is just wxy is equal to 1 if x plus y is at most 1, and otherwise it is 0. And so if you look at the graphon in this form, then the topological space that we get from this metric is just the unit interval. And there is a nice metric which metrizes this topology. Now, what if I, for example, delete this row from the graphon? It's just a zero measure change. And I add, instead of this row, I add something which is constant 1/2. Okay? Now what happens is that I get, first of all, one point is deleted from here. So here is a missing point, and then secondly, there is a point which is far from everything, and I get this topological space. It's really bad. I didn't manage to recover this very simple topological space. So there is a nice way of helping this problem, and it's very natural. So I want to add all the rows that are missing, and I want to delete all the rows that are not there. So, okay, still let's go back here. So what is the problem with this line 1/2? Who has any idea? How can we decide that the row is not really a row in that graphon? There is a nice way. Yes? Anyways, so if you look at a small ball in the L2 topology of this row, a constant small enough ball, and you look at all the rows which are inside that ball, that's just itself. It doesn't contain any other row. So that means that the collection of points which are closer to this point than a certain constant value, that collection of points has zero measure. In this situation, just this set is just the point itself. So basically, you can decide this question in a way that if a point is not in the support of this measure here, then the point is not really a point in omega. You want to exclude that point. So this motivates the following formal definition. So we have this map omega to L2 of omega, say. And since we have a measure on omega, this map puts a measure here as well, the push forward of the measure. And then we take the support of this measure here on L2 of omega. So let T be the support. Actually, let me denote this by mu prime of mu prime. So once more, each point is mapped to its row, and then you look at the support of this induced measure here in the topology, which is just the usual L2 topology, and this support is a topological space which satisfies all our requirements. For example, in this example, it will recover the missing row and it will delete the superfluous row from the graphene. Okay. Turns out that, and I'm not going to prove these things because very technical. These are true, but not particularly interesting to prove. But the true fact is that the topological space, together with the metric and together with the measure even, this triple, is an invariant. It's an isomorphic, it's a graphon invariant, let's say. Graphon invariant means that if two graphons are weakly isomorphic, then these triples are the same. And in graph limit theory, we are always happy if we see something which is a graphon invariant, because that means that it fits well into the theory. Then we can analyze that notion with familiar methods. Okay, there is another fact here that if you represent any graphon in a way that you have a metric space J with a measure mu, and it's a complete metric space. Such that the metric here coincides with the metric induced by the graphon. Yes? So if you have any set, you look at the preimage under this map, and you compute the measure of the preimage. That puts a measure on this topological space. Such that the measure J is equal to the measure induced by the graphon. Sorry? Oh, the measure. Then we call this a pure graphon, first of all. And the nice fact is that once you have a pure graphon, then it is basically represented on its associated topological space. So if you compute this topological space T, then it is the same as J. Oh, full support. Sorry, that's an important thing. Yes, that's one of the main things. Plus support. There was a question. Yes. Sorry. What? B? B? So D is always defined on the vertex of the graphon. Okay, so if you define the distance d on an arbitrary graphon without doing this transformation, then it's not a graphon invariant, of course. But if you take the pure representation of a graphon, if you take any pure representation of a graphon, and then you look at this thing, this distance d inside the pure representation, then it will be a graphon invariant. Okay, so that's a nice property of pure representations, that they recover this, they immediately give this topological space. This is basically a tautology, actually, this fact. It's just stating the same thing in another form. But so we can talk about graphons which are already nice, which are already pure. And the graphon in my first example, which came from the unit sphere, is actually a pure graphon. It's easy to see. Because the metric is a nice metrization of the sphere that you get that way, and it's obvious, check it at home. So it's a pure graphon. On the other hand, if you represent, anyway, so. Okay, so now I'm going to define the second topological space that I promised, which is more related to my second example. Yes? Sorry? Yes. So the graphon is defined on a complete metric space. The metric is actually the same as the metric induced by the graphon. And the measure mu has to have full support on this metric space. The measure mu on J. Sorry? Metric, sorry. So the metric has to have, so the metric is the same as the metric induced by that. That was the other condition. This is just one if two vectors have positive, non-negative scalar product and is zero otherwise. So basically the intuition is that if 2 points are close, then their neighborhoods are almost the same. The fact about it is that this J is the same as this T. And this is a triviality. Sorry? So pure graphon is a definition. And the fact is that this is the same topological space. Okay? No? Not that thing? So the fact is that every graphon is weakly isomorphic to a pure graphon. That's a fact. Yes, and this is the construction, exactly. So what we have to remember from this is that every graphon is weakly isomorphic to a pure graphon. Okay. I promised you a second topological space related to a graphon. This is the following. Whenever you have a graphon W, you can take the square of W as an operator. Each graphon is an integral kernel operator, and you can just simply square this. Okay? So this is exactly the graphon which is the square of this integral operator. And we have that this new graphon, W circle W, is again defined on the same space, omega. It just puts another graphon into the same space. So what if we take the distance related to the square graphon instead of the first graphon, and we take the topological space generated by this. Now it turns out that this new graphon has always a compact topological space. It has much nicer properties than the first topological space. So I have this triple P d mu, and this is always compact. And in fact, there is an even nicer property of this metric space. Basically, the property is that if for every epsilon there exists some number k epsilon such that you can cover almost all points, like most points of this metric space by k epsilon balls of radius epsilon. And the exception is just a set of measured at most epsilon. And it does not depend on the graphon, this k epsilon. This is true for every graphon. You take the graphon, you take the square of it as a kernel operator, you compute the topological space, and it will have this property. Now this property is related to another nice fact, which is the same thing but formulated in a different way. I'm telling you this because maybe, so these will be basic facts from analysis which are not really well known. And they are not well known because they turn out to be equivalent with the regularity lemma, actually. So the fact is this: if you have a two-variable measurable function, W, then it can be always approximated by a step function with an arbitrary precision. So this is a step function when you decompose the unit intervals, say, into small intervals, and then the value depends only on the partition set containing the coordinates. So every W can be approximated arbitrarily well in, say, L1 by a step function. This is a well-known fact. It's a basic fact in analysis. But it's also well known that the number of steps that you may use will depend on the graphon. So if you fix an epsilon and you want to get such an approximation, there is no fixed constant such that you can always approximate the graphon with a step function of that many steps. Okay? It can get, the complexity of the approximation depends on the graphon. But on the other hand, if you take a W, which is the square of a W, which is the square of another two-variable function in this operator sense, then there is a uniform bound on the number of steps. That's an interesting fact. So if this is a square, then there is a uniform bound on the number of steps in terms of epsilon. Okay? This is somewhat surprising, right? And this is, it turns out to be equivalent to the regularity lemma, this stuff. That's important, yes. So here, the step function is used in this more general sense that these are measurable steps. Okay? Right? Yeah. L1 norm or L2 norm, these two things are equivalent. This is somewhat surprising, right? So that you can formulate the regularity lemma in this simple analytic form. Yes. So all that I'm saying is about bounded functions. Now good. So this fact is related to this compactness of this metric space. And it turns out that this new space related to the square of the operator W is that contains the previous metric space. So in other words, if you square W, then its topological space can only grow. So once more, I have W and I have the related topological space T. I have W circle W, and there is the topological space T prime. And the thing is that T is a subspace of T prime. It turns out that if W is already pure, say, we can assume without loss of generality that it's pure, because both things are invariant under weak isomorphism, say it's pure, then it turns out that all the rows are also different in this topology. They have a non-zero distance. But you may get new points added to the topology. So that's an interesting phenomenon. But if this space is compact itself, then you don't get new points in the topology. Well, no, because the thing is that this is a graphon invariant. So what I'm saying is that you construct the unique topological space T from a W with that process I described. And okay, if it's pure, then W, okay, so why I want to use that is pure is that I want to relate the two metric spaces. So actually I can already assume that W is defined on this space. If W is defined on this space and you take the operator square of W, then it puts a distance on this space, a modified distance. And it turns out that according to this modified distance, all these points are necessary, but you may get extra points. And the extra points will have just zero measure by the way. Okay, so this is the other topological space which is necessarily compact, and the two things are equal if and only if the first thing is compact. And it turns out that you can represent W as well on this new topological space T prime. And that's another natural representation that we sometimes use. Now good. Why is it interesting? Why do we consider topology? Well, the metric is what you get on the sphere from the L2 embedding. If you do that embedding, did I do that with L2? Yes, I did. That's very good. You just basically recover the original L2 metric on the sphere. Sorry? In the space of the special example of the sphere, you basically get the same metric for a special reason. Because, okay, so let me go back to the sphere example. So each point is connected to those points which are on this semi-sphere, right? So basically, if you take the characteristic vector of this neighborhood, it's a vector in L2 of the sphere. So if you look at the vectors corresponding to points, then you get a nice embedding of the sphere into L2 of the sphere, which is symmetric. It's actually the automorphisms are preserved here. So basically, the metric that you recover is the original metric on the sphere. If you take the second power of this operator, then you may get another function on the sphere, but you recover the same metric. But in general, you are right that if you look at this graphon, then it induces a different metric. What I'm saying here is not that the metric is also a restriction here. What I'm saying is that the topological space induced by this metric contains the original topological space. So I have little time left, but I really want to say a few words about the applications of this topological space, because that's more important than the little details here. So why do we consider this topological representation of the graph? Sorry? Yes, this is always compact. And actually, this compactness comes from the fact that weak convergence in L2 is compact. And actually, when you take the square of the operator W, this is like, it establishes the weak topology on the rows of the pure version of W. That's the main, the hidden thing. So one sentence about this topologization is that if you are familiar with ergodic theory, then in ergodic theory people study measurable dynamics, but it's a very important tool that you can put a topology on these dynamical systems, and you get topological dynamics. And there is a similar story going on with graphons, that you start with general measurable objects and you want to get a topological version of this theory. And there are several advantages of this topologization, which are the following. So the first thing is that actually it helps in the calculations. When we wrote this paper with Laci about finitely forcible graphons, then there were certain calculations when you could recover a certain algebraic structure on a graphon, on the points of the graphon. So say you can recover some group operation or any type of algebraic operation on omega. But if this operation, if the algebraic identities are only satisfied up to a zero measure set, that's pretty bad. Because if you have a two variable operation, say a group operation, which falls up to a zero measure set, because the operation is a two variable operation, it can be that the zero measure set is somehow diagonal, and you cannot just delete a zero measure set of points from omega to cure this problem. So it was a technical, it was really a technical thing when we were basically forced to introduce this topological representation, and then all the calculations became much nicer. Like you get perfect algebraic identities, and and this we really used. So the reason here is that because you get perfect algebraic identities. Let me tell you a very simple algebraic identity. I mean, this is just vaguely related to the algebraic identities that I told you about, but here is, for example, a very simple thing. If you take these restricted homomorphisms, and actually let's be very concrete. Triangle with one label in W. So this is this restricted homomorphism density that I introduced, and this is a function from omega to the 0, 1 interval. It's not a single number, it's a function. So now if the graphon is pure, then we know that this function is continuous on the underlying topological space. And since it is continuous, if it is constant almost everywhere, then it has to be constant everywhere, for example. But it is also true that if you say introduce two labeled points that are not connected, then this pxy is a continuous function on omega cross omega. And so on. So these continuities, these are really useful in the calculations. But anyway, there are many useful things here. The second advantage is that you may ask, when you solve a combinatorial problem in the limit, then it helps you to identify the actual topological space on which the example exists. So helps in identifying a nice representation. So for example, you solve an extremal combinatorial problem, and it turns out that the graphon, the solution, is something really fuzzy, fractal like the graphon, then you may still think that it's not the right way of representing it, and that there is maybe a three-dimensional representation which you cannot force into a smaller dimensional space. So this is also an advantage. The third advantage is that with the help of these topologizations, you can introduce the automorphism group of a graphon, and it turns out to be again a nice notion. I just say a few words about that. So the automorphism group of a graphon is a tricky thing because I mentioned this example with the constant 1/2 graphon. Basically, you may have many automorphisms. But here, you can take any measure-preserving action, and that preserves the graphon. It's a really ugly group. If you take this representation with the 1-point set, this is a much nicer group. It's a trivial group. So it turns out that if you take the pure representation of a graphon, then the automorphism group becomes a compact group. Which is a really nice and somewhat surprising fact. And since the pure representation is weak isomorphism invariant, the automorphism group in that sense is weak isomorphism invariant. So you get a notion which is very robust. So we define the automorphism group of a graphon as the automorphism group of its pure representation, which is a unique object. Now let me, unique, almost unique. So we still have a little zero measure problem with the pure representation, but it's much more well defined than W. Since the pure representation is defined with up to a zero measure problem with each row. So you still can have a zero measure problem in single rows, but you cannot have a zero measure problem which influences a row in a positive measure way. And that already allows you to define the automorphism group in a unique way when you have that pure representation. These are technical details. But I just want to emphasize is that this is always a compact group. In particular, if the graphon is vertex transitive, then since the automorphism group is compact, then it turns out to be a compact graphon. So in particular, so W is not transitive. If out W acts transitively on J, which is the pure underlying space of the pure representation, and such graphons are always compact. So this implies that J must be compact. Somehow, the funny thing is that the first few finitely forcible graphons, I also mentioned these finitely forcible graphons, were compact graphons that we were able to construct. I mean, the first few that are not step functions. Step functions are always compact. The underlying topological space of a step function is just the discrete topological space, finite topological space. But even our later examples for finitely forcible graphons were defined on a compact topological space. And we conjectured with Laci that this is always the case, that finitely forcible graphons are compact. But a recent result by Roman Glebov, who are Daniel Kral, and where is Roman? You. Thank you. So that shows that this is not the case, and there are algebraic points, I mean finitely forcible graphons, which exist on more complicated topological space. It's a beautiful paper and very surprising. So it shows that these very crazy topological spaces can, I mean, these are not just not compact, but not locally compact, these topological spaces. So these are quite crazy, and they can come up in extremal combinatorics in a natural way, which is really shocking to me. And I have to stop, but so there are many interesting issues about this automorphism group, how they are related to spectral decompositions and various facts, but I ran out of time, so thank you very much. So an automorphism group is an isometry of this pure representation J, which satisfies the following property. So basically, it has to satisfy that V phi is the same, W phi is the same as W with a zero measure mistake in every row. So that's the, since rows are defined up to a zero measure mistake, it can, when you apply this isometry to the set J, it may make a zero measure mistake in each row, but it cannot make more than a zero measure mistake in each row. That's the definition. What's that? My intuition is that you can do pretty much everything. Almost every reasonable topological space can be represented by a graphon. And so the idea is that whenever you can put whenever the topological space is metrizable, then and you can put a measure on it which has full support, that gives you a pure graphon with that topological space. I guess this is true. But you need a measure which has full support. Yeah. The metric itself, yeah, is the value of the graph. So Wxy is the distance. Any other question? Okay.